Good evening, everyone. Welcome to another exciting CO2 India webinar. I myself is very excited to listen to Professor Surya Prakash, who is known as the father of methanol economy, the concept and the real idea. So let me first introduce Professor Surya Prakash, and then we'll request him for the webinar. So Professor G.K. Surya Prakash was born in Bangalore. He earned his BSc honors in chemistry from Bangalore University in 1972 and MSc from IIT Madras, Chennai in 1974. Professor Prakash came to US in 1974 and joined Professor George Olah at Case Western Reserve University, Cleveland, to pursue his doctoral work. He moved with Professor Olah to the University of Southern California, USC, in 1977 to help establish a local hydrocarbon research institute and obtain his PhD in physical organic chemistry at USC in 1978. He then joined the faculty of USC in 1981, and he is currently a professor and the holder of Professor Olah Nobel Laureate Chair in Hydrocarbon Chemistry at the local Hydrocarbon Research Institute and Department of Chemistry. He also serves as the director of the institute. His research encompasses superacid, hydrocarbon, synthetic organic chemistry, organosilicon, and organofluorine chemistry, with a particular emphasis in the area of energy storage, which include batteries and fuel cells, greenhouse gas capture and use, and renewable fuels and catalysis. He is a co-proponent of a methanol economy concept based on carbon dioxide capture and recycling. He co-invented the direct oxidation of methanol fuel cells. He trained more than 150 doctoral and postdoctoral students. He is a prolific author with 820 peer-reviewed publications holding more than 100 patents. He has published 14 books. He has received many awards and recognition, including 3 American Chemical Society National Awards. He also received some of the very important awards from India, like 2010 CRSI Medal from the Chemical Research Society of India. He also co-shared with the late Professor Olah the $1 million USD 2013 Yerrick and Shell Sampson Prime Minister's Prize for Innovation in Alternative Fuels for Transportation. In 2015, he won the Henry Moissan International Prize for Excellence in Fluorine Chemistry. He is a fellow of American Association of Advancement of Science, member of European Academy of Arts, Science and Humanities, a fellow of the European Academy of Sciences, foreign fellow of National Academy of Sciences, India, and fellow of American Chemical Society. He also sits on editorial boards of several international journals. Professor Prakash authored a book with Professor G.A. Olah and titled Beyond Oil and Gas, the Methanol Economy, which received worldwide attention and now become one of the key key idea to really capture the CO2 and convert into useful chemicals. And I think today he's going to talk about the methanol economy, the idea, concept, and how he really made that happen. So we are all very excited to listen to you, Professor Surya Prakash. Thank you very much for joining that early in the United States, and I kindly request you to start your webinar.
Yeah, thank you very much for that kind introduction, Professor Polishetivar. And it's a great pleasure to give this webinar. Good evening, ladies and gentlemen, and good morning for my friends in US. And it's been a pleasure talking about this subject to friends in India. The title of my talk is Long-Term Sustainability.
Excuse me, Professor Olah, we are not seeing your slides now. We're seeing this video file. So
okay. Oh, I see. Okay, let me see. Let me go back to the stop share and come back again. Okay.
Yes.
You're not seeing the. Oh, I see. Okay, interesting. Now you can see it.
Yeah. Now it's perfect.
Okay. The title of my talk is the long-term sustainability through carbon dioxide capture and conversion, the so-called methanol economy concept. And what are the problems we are facing in the modern world? There is increasing world population, and of course, there is increase in standard of living, especially with the wide internet and access to information. Everybody wants to achieve the standard of living of an average American, all over the world. And most of the standard of living has improved because we have been using what are called fossil fuels. Fossil fuels are fuels made of carbon, mostly carbon, oil, gas, and coal. They're called hydrocarbons. They have different range of hydrogen and carbon ratios in natural gas, oil, and coal. And since the dawn of the 18th and the 19th century, actually, I could say, the 19th century, we discovered oil. Coal has been used for, past several hundred years, 500, 600 years all over the world in large quantities. And of course, natural gas, we started using in the 19th century. So we basically using all this finite sources, so-called fossil fuels made of carbon, and indiscriminately burning to produce energy. Of course, when you burn hydrocarbons, the carbon ends up as carbon dioxide, the hydrogen ends up as water. And of course, there's increase in carbon dioxide content in the atmosphere, so-called the greenhouse effect, the global warming. Currently, the CO2 concentration in the air is 420 parts per million. That is 0.042%, okay? Very little, puny, compared to other gases like oxygen and nitrogen in the air. There is more argon in the air. In fact, there's 1% argon in the air. I call CO2, this low concentration, it's a miracle molecule. Without CO2, there won't be life on Earth. We all know that, right? So this is a very important, molecule for sustenance of life. So we cannot just say, let's get rid of CO2 and forget about it. We can't do that. CO2 has to be managed, okay? Now, what are the problems we have? If you look at the history of the world, in the 1650, the world population was about close to 500 million, and it's steadily increasing. In 2011, we surpassed 7 billion. In fact, if you look at there is a thing called Worldometer with the United Nations. In 2022, the world population is almost 7.9 billion. By 2050, if you talk to a pessimist, he will say we'll probably, equilibrate around 11 billion people. If you talk to an optimist, it may be around 9 billion, okay? So the population of the world is going to increase, whether we like it or not. And all the population in the world, actually, especially the people in the, the developed countries, use enormous amount of energy for all their activities. In fact, you can kind of come up with an energy number for the world, what we are currently using. In fact, we are using 18 terawatts continuously, the power. A terawatt, is a 10 to the power 12 watt, okay? That's tera. And it's equivalent to 18,000 power plants, which produces 1,000 megawatt continuously. That's what Earth is using, all energies. You can think of transportation, electricity, agriculture, whatever, okay? And it's supposed to go up by 21 terawatts by 2025 and 30 terawatts by 2050. So this is the problem we have. We need enormous amount of energy. So how are we going to cope with it? Of course, if you look at a lot of statistics, okay, the key world energy statistics put out by IEA, International Energy Agency, in 2016, this is a good number, actually. More than 80% of our energy still comes from burning fossil fuels. The coal is decreasing, although countries like India and China are still burning quite a bit of coal. Oil is also being used enormously. And the natural gas use has increased in the world because we have found a lot of natural gas, especially in the United States with the shale gas. Discovery, there's plenty of natural gas. And of course, if you really look at it currently right now, we are facing a big problem with Ukraine, with a war, with Russia. And all the Russian natural gas, politically, oil, there's a lot of issues with it. So the prices have gone up too. In fact, if you really look at, what is costing natural gas, it used to be $3. Now it is now $12 and things like that. Even the oil prices, the barrel of oil has surpassed more than $100, 120, 130 sometimes. Okay. So, but still we are using fossil fuels all over the world. If you look at other than carbon, hydro and nuclear, which are non-carbon based, they are not very much. And renewables we talk about, like biomass and other combustibles, waste and all, it's still about 10%. Okay, I'll come back to this a little bit later. So if you really look at it, we are still using quite a bit of this carbon-based fuel for energy production and sustenance of our technologies and life and things of that nature. What are fossil fuels? Fossil fuels were produced on Mother Earth over eons. All the decaying, plant and animal matter under the pressure of the earth, deep in the earth's, mantle. Actually, it's about several, miles depth, you could say, half a mile to several miles depth. It got buried. And in fact, if I really look at it, I would define fossil fuels as fossilized sunshine. All the energy for the creation of fossil fuel came from sun, And so this fossilized sunshine created over eons gave us unprecedented prosperity and growth to humankind in the past several centuries, with the dawn of the Industrial Revolution. This is what the problem is. Now, of course, humankind, they're utterly dependent on petroleum and other fossil fuel products as chemical feedstocks also. In the United States alone, even today, ladies and gentlemen, around 65% of energy, our transportation comes from burning gasoline, diesel, and jet fuel, etc. So transportation sector is utterly dependent on petroleum oil, more than 90%. But what people don't talk about is 5 to 10% of petroleum is also used to provide a vast number of essential products such as plastics, fertilizers, medicines, etc. Okay, so it's very important. So we cannot say time out carbon. Okay, it's not possible. Okay, we need carbon because you and I are made of carbon. Remember that. So we cannot divest from carbon. I'll come back to this later. So besides CO2 emissions, fossil fuels are also finite, non-renewable, and therefore unsustainable in the long run. Now, what's happening, with all this burning fossil fuels, basically burning coal, petroleum, natural gas, cement production, which is used. You calcinate calcium carbonate to make calcium oxide, which is the principal component of cement. And gas flaring, when you burn natural gas and all that, you produce an enormous amount of CO2. And believe it or not, in 2013, we surpassed 35 billion tons of CO2, called anthropogenic CO2 emissions. And in 2017, it surpassed 40 billion tons. So we are increasing CO2 production by burning all these fossil fuels. And the problem with CO2 is half the CO2 emissions accumulate in the atmosphere. And that is more than 20 billion tons per year, contributing to global warming, glacier ice melting, sea level rising, etc. And half of it also dissolves in the ocean. And when you dissolve carbon dioxide in the oceans, you form carbonic acid. The pH level of the ocean is going down. That means you are acidifying oceans. So the coral reefs, which are also made of calcium carbonate, limestone, is being destroyed. When coral reef goes, all the the ocean ecosystem gets affected. Okay? So we also have this is a major issue with CO2, excess CO2 in the atmosphere, as well as dissolved in the ocean. Now, if you really look at people who model, they have modeled this, how much CO2, what it contributes, and all that. Carbon dioxide is one of the major culprits. About 60 to 65% is carbon dioxide, which is contributing to global warming. That is 1.82 watt per meter squared. Okay, this is what the estimate is. And total present anthropogenic radiative forcing is about 2.83 watt per meter squared. And freons, which are used to be used for refrigeration, halogenated compounds contribute about 13% for the global warming. These are man-made chemicals. And nitrogen oxides is about 6%, which comes out of emissions of your internal combustion engine. When your gasoline and diesel engines are burning hot, they also oxidize nitrogen to nitrogen oxides. So this is also one of the big contributors for global warming. It's not just CO2 alone. Nitrogen oxides are also a big issue. They're called NOx, nitrous oxide, nitric oxide, and things of that nature. Of course, natural gas itself, methane, the principal component, is also a very global warming gas. It contributes about 17%. Because when you're exploring natural gas, shale gas, and all, there are leakage. It's called seepage. And also, any decaying organic matter with bacteria, you can produce methane. In fact, gobar gas, they call in India, right? With cow dung, we produce gobar gas. So that's also methane. And with leaks, it also contributes to global warming tremendously. And also countries like India, which cultivate a lot of rice paddy fields also produce quite a bit of methane. So organized agriculture for 8,000 years also produced greenhouse gases, okay? So we should be aware of that. And also there are these hydrofluorocarbons, which are used as refrigerants. For example, HFC. Can you see this thing moving, my cursor? Can you see the cursor? Okay. HFCs, they're called. Fluoroform is 12,000 times, more global warming potential. Methane is about 23 times. NOx is about 300 times more than CO2. So all these are big issues, okay? And sulfur hexafluoride, which is used in transformers, 22,000 times more global warming potential. And they also linger in the atmosphere for a long time. They're not destroyed in the atmosphere, okay? So these are big issues with, this global warming gases. And CO2 is one of the major contributors. That's what we are focusing right now. The rest of this stuff, with technology, maybe we can solve it, production of methane and things like that. We can reduce it. Of course, we have banned halogenated compounds because of the Montreal Protocol with ozone hole formation and all that. And of course, we can design better engines. That's where methanol economy also will come in. We can have engines which are burn cooler. So that way you don't produce NOxes, nitrogen oxides. Now, one of the things we talk about CO2 problem is, why don't we collect this CO2, separate it from air? It's only 0.42%. So you need to know how to capture CO2 out of air. And then once you collect it from point sources, can you just bury it in coal beds, or depleted natural gas fields, or depleted oil fields, or deep aquifers, or even under the ocean? Okay, it's called carbon capture and sequestration. It's a technological solution, okay? It's basically an engineering solution, I would call it. Okay, so you collect it. But collecting CO2 is pretty expensive, okay? Because you need to separate from all kinds of, in coal burning power plant, you get about 8 to 9% CO2 in the air, but it has a lot of noxious compounds like, sulfur oxides, and, heavy metals and things like that. It has to be separated and, buried and all that. I'll come back to this in a minute. So if you really look at it, just to give a picture, how much of fossil fuels are we using every day? About 100 million barrels of oil is consumed every day right now. A barrel is 42 gallons or 160 liters. Enormous amount of oil is consumed, and it's converted to, petroleum and diesel and things like that. 11 billion meter cube of natural gas is used, and 20 million tons of coal is used for producing energy, mostly in countries like China, India, and other places. And China produces enormous amount of greenhouse gases. In fact, China currently is putting out 10.6 gigatons of CO2 every year. India is putting around 2.4 gigatons. United States currently is about 5.22 gigatons. Okay, just to give you the major culprits in this, the CO2 saga. Okay, these are because we have big population, and India is much better, but China has become a manufacturer to the world. They make everything, right, for us. So that's why China produces a lot more CO2. And if you look at alternatives people talked about, even in India, there is people talking about, we have India, one of the largest sugar producers. So why can't we make ethanol? United States converts, for example, corn into ethanol, the corn starch into ethanol, and US uses 40% of its corn crop to make ethanol, bioethanol, okay? And we produce 17.3 billion gallons of ethanol is produced per year. This is 400 million barrels from corn, equivalent to 270 million barrels of oil. So 2.7 days supply. So there is a proverb, actually, I will quote, maybe, for Ravanasura's stomach, it is half a annas of buttermilk. Okay, a buttermilk worth half. Anna is an Indian term, for half anna or half a paisa or something. So it is very small amount. Okay, 2.7 days supply. In Canada, there's a proverb called Ravanasurna hottege aru kasina majjige. That's the Canada equivalent. Okay, so very, very little, and we are sacrificing 40% of the corn crop, which would save the world. Because corn is a food product. You can't just, we are burning food. In Brazil, 7.5 billion gallons of ethanol is produced in sugarcane. And biodiesel requires a lot more land and all that. Oil is also very expensive. As you know, sunflower oil has gone up in prices. In India, there's a big riot because the cooking oil, Ukraine used to be the big producers of cooking oil, and we can't import it anymore. And palm oil too from Indonesia, they have stopped it. So all these things, oil, nature puts a lot of effort to make, cooking this vegetable oils. So these are all the issues we had to talk about. So biomass fixation by photosynthesis, if you look at nature does it, takes CO2 and water with chlorophyll, the green dye and sunlight, makes all these sugars, cellulosic materials and all that. So you can talk about biofuels like ethanol, butanol, vegetable oils, but it can only be a small percentage of energy mix. With almost 7.9 billion people in the world, we need food security over energy security. That's more important. Okay, we can't burn food. Okay, we have to be careful with biomass. So you also have, but to biomass, you have to look at land availability and use. We don't have enough land mass. Water resources, irrigation is a big issue. You think fuel is a problem. Water is a bigger problem with droughts coming all around the world with climate change and all that. Even countries like India, in certain parts of India, we have more rain, certain parts, no rain. Ativrishti, anavrushti, we say in Sanskrit, right? So we had to worry about food security, energy security, fertilizer use. We make crops with chemical fertilizer. We need to produce urea. How do you make urea? You take CO2 and ammonia. How do you make ammonia? From hydrogen produced from fossil fuels, natural gas reforming. So these are all the issues we need to talk about. So processing technologies, life cycle analysis is all important when you make a fuel or a feedstock. So overall energy balance. So I'm being a little bit, kind of pessimistic, but let's be optimistic, because sun is the source of all energy on Earth, right? Sun is going to be there for next 4.5 billion years. And sun is giving out tremendous amount of energy it is putting on Earth, almost 173,000 terawatts continuous. It's a reliable nuclear fusion reactor, okay? So we need not worry about it. Now, what are the issues? Why not use more alternative energies and resources? Of course, hydropower is based on sun's energy, water cycles. Geothermal energy, which is, creation of Earth's mantle, there is a lot of heat. We can extract that. Wind energy is also because of sun heating the wind. So wind energy is, being used. It's increasing every day. Solar, of course, the solar energy to make electricity. Biomass, ocean energy, which is gravitational, and of course, nuclear energy. It can make, I'm talking to folks at Baba Atomic Energy Research Center. Nuclear should have some, role to play because it's carbon free, as long as we can make sure it's safe. So the problem with alternative energies is cost, but some of these are coming down rapidly, especially wind and solar. Still, fossil fuels are still the biggest bargain nature gave us, right? Ever gave us, because you make a hole in certain parts of the world and the oil and natural gas gushes out, okay, even today. The most promising solar and wind are intermittent and fluctuating. So only solar energy is produced, electricity is produced when sun is shining. Wind energy is produced only when wind is blowing, right? It's intermittent. So we need to store energy to balance the grid and all that. So storing electricity on large scale is becoming an issue. Battery technology has not advanced. It's also getting very expensive. Even with batteries, when we talk about as a solution, we have to look at the life cycle of battery. To manufacture a battery, to extract lithium metal from lithium ore, and all the energies we calculate, it's as bad as running an internal combustion engine, okay? So you have to look at whole life cycle when you talk about all these other technologies. Now, this is a very important slide. As I said, sun is going to be there for next 4 billion years, okay, 4.5 billion years. If you look at terawatt year equivalent, solar is giving 23,000 terawatt year equivalent energy continuously. So these are renewable. This all in yellow is renewable. Even wind is 70 to 120 terawatt year. This is a scale I'm using. It's called terawatt years, continuous, energy. If you look at fossil, all the fossil energy that is available in Earth is only 215 terawatt year for natural gas. Petroleum is only 240, and coal is about 900. So compared to sun, these are puny. Okay, and uranium, especially U-235, the fissionable uranium, is equivalent to 90 to 300. Okay, so it's not very much if you really look at it. Okay, so everybody you talk to, for example, talk about the solution for our problem is to go away from carbon. So everybody talks about the other thing called the hydrogen economy. Why can't we use hydrogen for everything? Of course, hydrogen economy is clean. When you burn hydrogen, you make water. You can use hydrogen as a fuel in fuel cells to make electricity. It's true. But the problem is, on Mother Earth, hydrogen is not a primary energy carrier. It has a very low boiling point, minus 253 degrees. So you have to go to low temperature to make it a liquid. It's tied up in water and fossil fuel, so it has to be liberated. You need energy to do that. It's incompatible with 20% of oxygen in the air. It has a love affair with oxygen. It can catch fire, okay? It can explode, okay? And liquid hydrogen, even if you make it with a lot of difficulties, has 1/3 volumetric energy density of gasoline. Okay, this is a big issue. 2 grams occupy 22.4 liters, okay? So high pressurization is required. So you have to put hydrogen at 10,000 PSI pressure to carry any substantial amount for a car. For example, Toyota Mirai carries 4 kilograms of hydrogen at 10,000 PSI pressure in a carbon composite tank. Very expensive technology. Because all metals which have carbon in it, beyond 5,000 PSI, hydrogen makes it brittle. Metals become brittle under high hydrogen pressure. So this is a big issue. Infrastructure is very expensive. Hydrogen diffuses easily, highly flammable, forms colorless flame, okay? So why can't, as a chemist, as an organic chemist, for me, carbon dioxide is a fantastic feedstock. It has already carbon built into it. It's a gas, it's available. So CO2 is already utilized as a feedstock to make many, many chemicals. For example, they make polymers, polycarbonate, polyurethanes. Of course, you can make methanol, formic acid, methane, dimethyl ether, dimethyl carbonate. It's used to make urea, one of the biggest chemical commodity product made by humankind. Close to 200 million tons a year is ammonia and CO2 make urea. CO2 is used for oil recovery, natural gas recovery, methane recovery. It is used by beverage industry. Decaffeination, you make decaf coffee. You extract with liquid CO2. A lot of essences are also used to use liquid CO2. Dry cleaning, you do with liquid CO2 now. It's considered better than using hydrocarbons, okay? You can make organic carbonates, inorganic carbonates, carbamates, carboxylates, lactones, and all that chemical feedstock. Supercritical CO2 is used for refrigeration, dry ice, you already know that. Fire extinguisher, injected into metal castings. It's a respiratory stimulant. You and I won't be alive without CO2. CO2 is the trigger mechanism for your breathing. If air has no CO2, your breathing mechanism would stop, okay? So all these things are very important. It's an aerosol propellant and all that. So thinking about all that, we said that the solution for hydrogen economy and also for CO2 is combine CO2 and hydrogen, make a very simple molecule called methanol, called the methanol economy. And methanol economy was, we proposed this with my colleague George Ola, my mentor, for 40 some years. He passed away in 2017. He was an amazing chemist, and he got his 1994 Nobel laureate. He became a Nobel laureate for his superacid chemistry, carbocations, which I participated in that effort. And when he got the Nobel Prize, I went to Stockholm with him to receive the prize, and we had good relationship. That was my dad, in the United States. He took care of me for 40-some years. So we built an institute, and we proposed in the early 2000 what is called a methanol economy concept. So what is methanol economy? Using methanol as a fuel and feedstock. In fact, methanol, this unassuming molecule, is a liquid at room temperature. It's called the wood alcohol. This was discovered by Dumas, a French chemist. When you heat wood, you do what's called a destructive distillation. You get methanol, a nice liquid, very fragrant smelling. Only problem with methanol is you shouldn't drink it. It's poisonous to humankind. Okay. For bacteria and all, it's food. But for higher mammals, it's a poison because it makes formaldehyde and things like that in your body. But it's a fantastic fuel, high octane, clean burning, half the energy density of gasoline, 15.8 millijoules per liter. It can be mixed with gasoline in various proportions. I'll come back to this. It's an excellent fuel for IC engines. Methanol can be converted to dimethyl ether. It's a high cetane, clean burning diesel fuel. I'll come back to this too. And methanol could be directly used in a fuel cell, which we invented in the 90s. More importantly, in the 80s, George Olah and I did a lot of chemistry in this space, and many others too. Methanol can be converted to higher carbon products like olefins through a process called MTO, methanol to olefin process. You can make diesel, gasoline, aviation fuel all through methanol. So this unassuming molecule, very simple to make. You can make all the products that currently we use from petroleum oil. Now, what are the drawbacks? Methanol is miscible in water, is corrosive for certain metals. So you have to use compatible materials. Already we are doing it. It's similar to ethanol in many ways, water soluble. So whatever problem we solve with ethanol, we can also, methanol is already solved. Okay. It's a low vapor pressure at low temperature. So you need to spike it with gasoline. So you have to mix with some gasoline, not a problem. Ingestion could be lethal. Of course, in India, we have the huge tragedies all the time, when people are making ethanol, at home or something, brewing something. When they put wood at all, you can get methanol contamination. But how many times we go to a gas station and ask for a pint of gasoline or diesel to drink? It's equally toxic too. So we need to train people not to drink, but dispensing methanol and all is not a problem. But California in the late 80s, we used methanol gasoline mixtures because we had a smog problem. And we had no accidents at all dispensing methanol. Spillage to the environment is quite safe because all bacteria can destroy it right away. And also methanol is used to purify wastewater for denitrification of water. It's used as a reducing agent. So denitrification of water, people are already using tons and tons of methanol for wastewater treatment. There's an it's a very important report I came across recently called ICCT report, where compatibility of methanol fuel blends with gasoline vehicles and engines in Indonesia is produced by ICCT in December 2021. They talk about all the problems associated with methanol as a fuel. Methanol in internal combustion engine, it's a high octane fuel. It can be compressed to very high ratios. You compress gasoline in the air in an internal combustion engine, generally between 8 or 9 to 1. A diesel can be compressed 12 to 1. But believe it or not, methanol can be compressed 15 to 1. So when you combust methanol, you get very high torque. Okay, torque means power. Okay, this is very important. And methanol also has higher flame speed, so it gives you higher efficiency. More importantly, methanol has higher latent heat of vaporization. 3.7 times more than gasoline, can absorb heat better, removes heat from the engine, so you can use air-cooled engines, can be blended with gasoline in various ratios. And also because it is burning cooler, we don't make nitrogen oxides. Very little NOx. Since it's a one carbon alcohol, no soot, no particulate emission. So no particulate emission, no NOx. So it's a fantastic fuel, high octane fuel. Okay, burns better, less NOx and particulate matter. It's also very easy to extinguish methanol fires over gasoline fires because methanol is miscible in water. Water will extinguish methanol fires faster than gasoline fires. Gasoline fires, you need foam. So that's why methanol was used in race cars. Performance was high. If there's an accident, they can extinguish it with pouring water. You don't have to find foam to extinguish the flame. So these are all, very interesting aspects of methanol. And the methanol could be dispensed in regular gas stations. For example, these are all a race car, a taxi fleet in China, buses in China, dispensing methanol. In fact, China is one of the biggest adopter of the methanol economy. 10% of the transportation fuel China is already methanol. Okay, I'll come back to this in a minute. In fact, all these provinces in China use methanol in various ratios with gasoline. This is a methanol filling station. Israel is using methanol. Iceland is using methanol in a plant, which we had something to do with. It's called Carbon Recycling International. I'll come back to this in a minute. And this is a regular call made by a company called Geely. Geely is one of the largest car manufacturers in China. They own Volvo, and they make 100% methanol cars, which looks like Volvo cars, run on methanol. In Israel, methanol fuel demonstrations, this happened many years ago. Prime Minister Netanyahu, when he was, he called the Fuel Choices Initiative. So they're already adopted in 2016, M15 fuels. Fiat and Door Chemicals are already using this, mixed fuels. India also came up with a roadmap, especially on 11th September 2015, Niti Aayog held brainstorming session on possible roadmap for methanol economy for India's long-term energy security. And they have formed groups, for expert groups, and the Methanol Institute has committed to help them. And in fact, I was involved in organizing this meeting in New Delhi in September 2016. And this is a latest from April 30th, 2022 Economic Times. Indian Oil rolled out brand new M15 petrol station in Tinsukia, Assam. So India, M15, even Gadkari made announcements on this recently, I believe. So India is also thinking about this idea. In fact, Kirloskar has, even demonstrated gensets using methanol, 100% methanol, okay? So modifying regular diesel engines, type gensets or gasoline gensets into methanol gensets. Now, in fact, the methanol can use diesel-like efficiency and torque with methanol. There's a group in MIT, Daniel Cohn. Methanol provides exceptionally strong suppression of engine knock, especially when it is directly injected. Higher allowed turbocharging pressure than gasoline or natural gas. Spark ignition methanol engine can provide 1.5 times more torque per liter than diesel. Amazing, isn't it? So a diesel engine 9 liter gives you 1,300 pound-feet torque. A methanol, same volume, gives you 2,000 pound-feet torque. So this could be a game changer, okay? For example, so you need a 15-liter diesel engine to produce 2,000 pound-feet torque. So you can make the engine smaller. The fuel you use methanol, you get the same torque. It's going to save a lot in manufacture, materials. In fact, diesel-like efficiency, people are talking about better tank engines, railway engines, all these kind of stuff you can do with methanol. In fact, there's a group in China that took a regular diesel truck. They start a diesel cycle and start injecting methanol once the compression stroke starts. So with $1,000 retrofit, they can use, your emissions become very clean. You get a high torque, engine. Marine sector, 300 and 400, close to 400 million tons of bunker oil, middle distillates are used for marine industry, ships. Everything is transported by shipping industry. And they produce a lot of particulate matter, NOx, sulfur oxides, and shipping industry can pollute the oceans, but nobody cares. It's international waters, right? But they're changing now. In fact, methanol as a marine fuel, the Stena, the third largest shipping line in Sweden, has converted diesel engines to methanol engines. Methanex, which has trawlers which use methanol as a fuel now, not bunker oil. And in fact, it's very easy to convert a conventional diesel engine to methanol engine. Just you have to put glow plugs or spark plugs in the engine. Maersk, which is the largest shipping company in the world, has ordered 8 large ships using renewable methanol. So these are all coming into play because methanol is a very, very good fuel for combustion engines. Dimethyl ether, which is made by methanol, is also excellent diesel substitute, high cetane number diesel substitute, very clean burning. It's already used in spray dispenser. It's non-toxic, safe, and does not form peroxides. It's a substitute for LNG and LPG, so you can cook with it very nicely. Easy to produce, ship, and dispense. It's already used for sootless flame, no particulate matter. In fact, all these trucks, all over the world have been shown to run on dimethyl ether. Of course, hydrogen can be used in a fuel cell, hydrogen oxygen fuel cell to make electricity. But hydrogen, I already told you, is very difficult to lug it around. You need pressure tank and all that, not so easy. Transportation is difficult. You can use methanol by reforming to produce hydrogen for a fuel cell. In fact, you can carry methanol on board and make hydrogen in quantity, okay? People are thinking about it. In fact, there are companies which are making hydrogen on board. So it's called range extensor. You have an electric vehicle, which gives you only 150 kilometers. But if you make hydrogen with a fuel cell, charges the battery on board, you can get 1,500 kilometers, called range extender. They're already thinking about such technology. So reforming is a process, very simple. Methanol and water, of course, you can do this conventionally, you get CO2 and hydrogen. So methanol stores about 12.1 weight % of hydrogen. Okay, more enormous amount of hydrogen, twice as much as liquid hydrogen, because liquid hydrogen density is pretty low. Okay, well, weight. So you can do this. In fact, my group has developed a lot of technologies in this area. Methanol, if you take a primary diamine, I can make a urea and produce 3 moles of hydrogen. So the carbon is not released. So it's a carbon-free hydrogen production, reforming to make hydrogen. And once you make urea or this formamates and all, this can be converted back to methanol with some catalytic processes. So at gas hydrogen stations, I can take methanol and produce hydrogen. I call chemical compressors. We have that technology we are trying to produce. So instead of making hydrogen, bringing it in a truck, I just send methanol to a hydrogen station and you produce hydrogen at site under pressure, things like that. We have thought about it, okay? So, this got a lot of interest when we publish such papers. So we are, you do water electrolysis, make hydrogen, make methanol. You can produce hydrogen by reforming at low temperature. My group has developed technologies where we can use reforming at 80 to 120 degrees. Usual reforming using heterogeneous catalyst happens around 230 to 50 degrees. So we can make it much lower, okay? So, and in fact, we have produced hydrogen up to 5,000 PSI pressure, almost like a chemical compressor. So we can do that too. So direct oxidation methanol fuel cell, is a very other important technology we have developed. So methanol can be oxidized at an anode at very low potential, coupled with an oxygen reduction at the cathode. So we can use a liquid methanol water mixtures to make electricity. At the end of my talk, I'll demonstrate this technology for you. So direct methanol fuel cell is much better than hydrogen because you can put liquid, 5 kilowatt hours per liter, the theoretical, efficient, the content, the energy content of methanol. It produces only water and CO2. We don't have to reform it. You can use it at even 0 degrees, 20 degrees, you can start up liquid feed of reactants. So no polymer dry out. This has already been commercialized by this company called Smart Fuel Cells. They're producing 70 watt hours to 3 kilowatt hours methanol fuel cell, lot for defense application. Okay, even Indian Army is using it at certain sectors, such a direct methanol fuel cell. You can also use solid oxide fuel cell with methanol. In fact, very easy to do at this temperature. In fact, Wärtsilä has, sells 20 kilowatt methanol solid oxide fuel cell stacks. Is used by marine industry. It's already happening. Methanol is also very good for cooking. China uses 1 million tons of methanol to cook because it's very clean burning. In India, we use kerosene in villages and all those in huts. Kerosene makes very bad soot, very bad for your health. Methanol is very clean burning. There are clean cook stoves. In fact, this is in Assam. The Niti Aayog demonstrated clean cook stoves, which was given by a NGO. Very clean, and even the people who made food, they said it tastes better cooking with methanol or kerosene. Kerosene has this bad smell. And methanol is also used in boilers to make steam in industry. In fact, China has 1,000 converted boiler units in China, consuming 1 million metric tons of methanol per year. In fact, in Assam, they're also thinking of drying tea using methanol heat, burning methanol, tea production and all that. But Assam is the one state which ONGC has a plant which produces methanol. You all know that, right? Yeah. And so you can also use methanol in turbines to make electricity. In fact, Israel has a 50 megawatt power plant in Eilat, very clean burning, producing power. It can be used in fuel cells, this phosphoric acid, molten carbonates, solid oxide, PEM, polymer electrolyte membrane fuel cells. Methanol can also be used cooking. In India, there's a lot of interest. There's a project called Project Gaia. They want to use methanol to replace kerosene. Kerosene is actually aviation fuel. Okay, it's used for airplanes. So I would rather use it for airplanes than to burn it in huts. We can use methanol. Methanol is used to make all kinds of chemicals. You all know that. Many of you are chemists here. Formaldehyde, acetaldehyde, polymers. Methanol also could be given to bacteria to make tofu-like product, animal feed. This ICI, Imperial Chemical Industries in 1960s, used to use methanol as a feedstock to make animal feed, a tofu, a protein product. 100,000 tons were produced, okay? But nobody's doing it now, but in 1960, they did that. So methanol is already produced in 100 million ton quantity worldwide. And the biggest producer is China. It's used to make formaldehyde, 25%, MTBE, which is a gasoline additive, methyl tertiary ether, 11%, gasoline blending, 14%, mostly in China. Even you can make biodiesel out of it, like methyl esters. Dimethyl ether is about 3%. MTO is becoming big, methanol to olefins in China, 25%. And there are a lot of other, applications too. More importantly, methanol can be made to ethylene and propylene over bifunctional catalysts, which we did a lot of chemistry in this. And once you make ethylene and propylene, ladies and gentlemen, you can make all the products we currently make out of, petroleum oil. China produces close to, 27, 28 million tons of olefins through methanol. Now, how do you make this methanol? Methanol is made from syngas, from coal or natural gas. You can do direct methane conversion. We have worked in this space. You can do biomass gasification, make methanol. Ultimately, we can make it from carbon dioxide reduction. From wood, natural sources. And if you go to outer space, galaxies and all that, there is methanol, huge methanol clouds wherever there is a nascent star. Nobody knows the origin of it, how this is formed in nature. Okay. So methanol is also 460 billion kilometer in diameter near nascent star. Huge amount of methanol. Of course, their concentration is low, but it's enormous amounts. Okay. And recently, last year, we wrote a report with, IRENA, International Renewable Energy Agency, a publication, an outlook on methanol, in 2021 January. So we classified different kinds of methanol. We talked about brown methanol, you make it out of coal, which is not good, okay? It's you haven't paid the carbon cost. Then there is gray methanol, blue methanol. Then you can have totally green methanol, okay? So it depends on gradations. You can read this report, it's already published. You just say IRENA methanol report, you can download it. So there are different, of course, methanol is methanol, okay? It's one composition of matter, but how it is made is very important. So Currently, it is made worldwide using what's called syngas, carbon monoxide to hydrogen to methanol. This is an exothermic process. It can also be made by CO2, 3 moles of hydrogen, you make methanol and water. Of course, in this space, there is an important reaction called water gas shift reaction. You make CO2 and hydrogen, CO and water. So these are all some exothermic processes, okay? So currently the methanol is used, large quantities is using 2H2 and CO to make methanol. And how do you make this syngas mixture? You take methane and water over nickel catalyst at very high temperature. You make CO and 3 moles of hydrogen, okay? This is endothermic by 49.1 kcal per mole. So they use it at 800 degrees. And CO and 2H2 is used to make methanol. The extra hydrogen that is produced is to make ammonia. So wherever there was an ammonia methanol plant, there was also an ammonia plant. And the CO2 that was produced was also absorbed to make, urea. So that's how the economics worked. So natural gas was reformed. Of course, you can also do partial oxidation to make syngas mixtures. And of course, there are a lot of problems with this chemistry. You can also do what is called dry reforming, where CO2 methane, you make 2 CO and 2 H2. So these are all, conventional processes to make, this syngas mixtures. Combination of steam reforming and partial oxidation of methane is something which our group looked into. It called autothermal reforming. In fact, we came up with a process called bi-reforming, where we take steam reforming and dry reforming. We can combine these equations. We take methane, water, and CO2. We get 1:2 ratio of syngas to make methanol. And our institute has developed a lot of technology in this space, a lot of interest commercially. Of course, these are all endothermic processes. This is endothermic by 157.5 kilocalories per mole. So we're using CO2 and water with methane to do this chemistry. But how do you get CO2 and water? If you combust methane with 2 oxygen, you get CO2 to water. This is exothermic. So what my group did was, we burned some methane, make CO2 and water, produce the heat. We use this heat to combine with more methane to do, this reforming. So we came up with a process. We take methane reforming with water and CO2 to make methanol. Overall, this is exothermic. So we came up with a very interesting combusting partial methane to make the heat. So using the heat and the products combined with methane to do what's called bi-reform. So you can produce not only methanol, syngas in the right ratio, we can also produce heat to make electricity. So, Gas Institute has done some good analysis. It's apparently very interesting. So methanol can also be made from coal. That's why China does it. China produces about 60 million tons through coal, but this produces a lot of CO2 as a byproduct. For China, this is import substitution. High ash coal, they're making methanol. In fact, I'm proposing this to India too. India has a lot of high ash coal. They can, for the time being, they can do from coal methanol and also sequester CO2. Methanol from biomass. Biomass can be converted to syngas and made methanol. In fact, you can take biomass and, at low temperatures make what's called biocrude, with little bit air and biomass combustion. And then biocrude can be gasified. In fact, lignocellulose, you can do fast pyrolysis. You get this condensate called slurry. And this can be gasified with pure oxygen. You get syngas, methanol, other liquids can be made. Paper manufacturing, you get black liquor, which is lignocellulose basically. You can do syngas, dimethyl ether. And in fact, people at Sweden has a plant which does 4 tons per day dimethyl ether. Biomethanol from glycerol, you can gasify glycerol, and make methanol, 200,000 kiloton capacity in Netherlands. Ultimately, methanol can be done from CO2. CO2 is considered a problem. It's a linear molecule, very stable, difficult to efficiently reduce. It's a trace gas, but we have found methods to capture CO2. CO2 comes out of many, many point sources, geothermal vents, fermentation processes, natural gas wells, cement plants, fossil fuel burning power plants, aluminum plants, steel plants, air itself. Steel industry also produces quite a bit of CO2 because you use carbon as a reducing agent for iron oxide to make iron, right? So there are technologies called absorption, cryogenics, membranes, algal and microbial systems people talk about, So there are a lot of methodologies. Now, what are you going to use, to capture CO2? Efficient capture from air remains challenging. CO2 transport for geological storage, people talk about. Mineralization, people talk about. You can inject it in, some minerals, so it becomes limestone and things of that nature. Capturing in cement, people talk about it. Tree planting, tree takes out CO2 too, but we don't have enough land mass to capture all the CO2. These are all some of the people talk about. But air is very challenging. So my group has, over the years, have looked at, CO2 is an acid, weak acid. So fundamentally, from a chemist's point of view, CO2 is an acid-base problem. If you have a base, you can capture CO2. Okay, no big deal. So we talk about weak bases like polyethyleneamines, which you can, put it over silica, fumed silica, which have high surface areas. So you can make, the silica impregnated polyethyleneamines, and this look like this nice powders, and this can capture CO2 by passing air over it. So polyethyleneamine CO2, the secondary amine reacts to make what's called a carbamate salt. So 2 nitrogen sites is required. 1 nitrogen makes the ammonium component, the other the carbamate component. But when you have water around, this reacts to make ammonium bicarbonate. So each nitrogen can capture 1 carbon dioxide or bicarbonate. So 1 CO2 per amine, half CO2 per amine site. So we exploited this under dry conditions. You get carbamate formation, and wet conditions, you get bicarbonate formation. In fact, this is fantastic. It not only captures CO2, ladies and gentlemen, it also captures water. So we have shown, one of our first papers published in JAX, we showed that, we can do total CO2 75 milligrams per gram of our material we produced. It is recyclable. We get CO2-free air. For a battery project, we developed this technology. And what's interesting is we have shown at dry conditions with some of our materials, 156 milligrams per gram of PEI. Humid conditions, 234 grams of PEI. This is an enormous capturing capacity, okay? Whereas zeolites and all, they do very little. They have a lot of problems. So we have shown this, we can do 1,000 cycles of adsorption, desorption from our material. And we can show 157 milligrams of CO2 per gram of this silica-based absorbents. And in fact, this looks like this. We have already licensed this technology for indoor CO2 capture. When people are working in large buildings, there are a lot of CO2 is produced. Almost, like 1,500 ppm of CO2. So the air handlers are taking this outside air and exchanging with inside air. With our technology, you can capture CO2 within the building, so we don't have to condition the air, cooling or heating as much. We save 30% energy cost. This has been done already. This 180 buildings worldwide are using this technology. And ultimately, CO2 could be captured, and you can electrolyze water with alternative energy and make methanol in one step. And once you make methanol, you can make everything from methanol. Okay, this is what we call the methanol economy. And of course, methanol, CO2 can be reduced from a variety of sources. You can use all kinds of reducing agents, boranes, silanes, metals, metal hydrides, organohydrates, water, even molecular hydrogen, which we prefer. And Professor Polishettivar has done some very nice work using magnesium metal, as a reducing agent and all that, And of course, you have to recycle. There's organocatalysis, metal catalysis, biocatalysis. There are thermochemical routes, electrochemical routes, photochemical routes. People are exploiting. There's a huge space, and there is so much work coming out. I'm really very happy that people are looking into this in a big way. So what we have done is CO2 we can capture in this, this kind of liquid amines called PHA, polyethylene hexamine, which is a big product made by industry. We bubble air, we can capture CO2. In situ, we can use homogeneous catalysts. You can make methanol. So you can make fuel out of air. directly. And my group published our first paper in 2016 in JAX, which got a lot of attention. So we can keep on doing this from air. And we can use simple catalysts, cobalt-based, Beller has done. We have done manganese-based catalysts for this homogeneous catalyst, all at low temperatures, because the heterogeneous catalysis to make methanol at high temperature has thermodynamic limitation. Per passage, you only get 30% per conversion. At lower temperature, the thermodynamics helps us, the equilibrium helps us. We get higher conversions. In fact, we have recycled catalysts using this ruthenium macho type catalyst. And we have shown that we can do this again and again, capture, conversion. We call integrated capture and conversion of CO2 to methanol. In fact, this tells you amine, CO2 capture carbamate, bicarbonate salts can be made into ammonium formate, and this can be directly converted to methanol. Even hydroxide capture, we have shown recently we could do that. And so this is a very, very simple idea, integrated CO2 capture and conversion systems. It gives you what's called a carbon neutral cycle. In fact, these are all, we have shown different types of catalysts, homogeneous catalysts we have looked at. I don't have the time to talk about. Maybe this is not the best forum to talk about, intricate mechanistic chemistry. But all these catalysts, especially this C1 and C2 type catalyst gives you very high yields of CO2 to methanol conversion. And more lately in 2020, we published a paper which got a lot of attention. We also did this in alkaline media. We could do this in ethylene glycol as a co-solvent. We can make methanol and keep on doing this again and again. Okay, it's an amine-free system, and we can do this CO2 capture directly from point sources, including air. We can make methanol. Of course, the carbon dioxide comes from many sources or the atmosphere itself. Even over heterogeneous catalysts, you can make methanol. You can do even electrochemically, you can make syngas. Such chemistry too, my group has developed. And more importantly, we've also shown that CO2 and hydrogen over heterogeneous catalysts in liquids at lower temperature, we can make methanol. Yields up to 90%. These are not flow systems, but these are batch systems. We were able to show that. These are just published in 2021. So hydrogen is easily made from electrolysis. If you have 4 cents a kilowatt hour energy cost, you can produce hydrogen about $2.6 a kilo. So it's the energy of the electricity, the cost of the electricity, what dictates. United States has a program to make hydrogen at $1 a kilogram. That's a DOE target. Then once we have hydrogen, you can make methanol. This is the chemistry. At 4 cents a kilowatt hour, we can make $1.80 per gallon. That's 3.79 liters US gallon. Okay. So these are all happening. In fact, in Iceland, I was involved in this. We have built a plant in Iceland, which I was one of the consultants, where we take geothermal electricity, water, and CO2, which comes out geothermal steam. They are making 12 tons of methanol. We call it Vulcanol, totally green. And we named the plant after George Olah Recycling Methanol Plant, CRI Carbon Recycling International, George Olah CO2 Renewable Methanol Plant. And this kind of an idea, people are thinking of mimicking worldwide. In China, they want to build 1,000 tons a day. And about 40 kilowatt hours are needed to produce a gallon of methanol. 11 kilowatt hours per liter. That's the energy requirement. Methanex and Geely are the major shareholders. So what I told you in the past 50 minutes or 50 minutes or so, this ubiquitous methanol is a fantastic fuel and feedstock. It can be made from natural gas, from coal currently, so we can adopt methanol. It can be made from biomass, no problem, but it can be made from CO2. Okay, that is captured CO2. So methanol can be converted to dimethyl ether. So I call this CO2 is a 1 carbon problem. Methanol is a 1 carbon solution. So I wrote a Kannada article for Niti Ayog magazine. Carbonina samasyege carbonindale parihara. Okay, for a 1 carbon solution, in a 1 carbon problem, 1 carbon solution. Okay, so this is called in American lingo KISS principle. Keep it simple, stupid, or keep it simple, silly principle. So it's a bridge fuel in the short term, methanol, and a renewable carbon neutral fuel in the long term. As long as human life is supported by Mother Earth, we can keep on doing this, because we need carbon-based products. We need medicines, we need fertilizers, we need plastics. So this is a holistic solution. So utilization of recycling CO2 from the air, anthropogenic carbon cycle mimics nature's own photosynthetic cycle. That's what we are thinking. So we can make carbon capture and recycling using all these alternative energies. We can store with carbon, make methanol, and keep on doing what we are doing. We don't have to change our infrastructure. I could be running my 1968, whatever Fiat car in India, because methanol is a much better fuel than gasoline for it. We can run our auto rickshaws on methanol, okay, no problem, things like that. So we don't have to, infrastructure change is very expensive. So if you don't have to change infrastructure, it's fantastic. So methanol economy is sustainable recycling atmospheric CO2 to fuels and material. In fact, this has been published in a book. A third edition came out in 2018. And this has been translated to 5 languages. And the Chinese government bought 55,000 copies of our book, okay, almost in 2009, and adopted the whole idea, lock, stock, and barrel, okay? So it was interesting. And just to tell you, this I gave a this quotation to a magazine in the United States. Methanol gives us a way to store not just kilowatt or megawatt hours of power, but gigawatt hours. I said it could be a game changer. So it's a way to store energy, ladies and gentlemen. So why are we not doing this in America? Maybe this is also true with India. Winston Churchill used to say about America, Americans will do the right thing in the end after exhausting all other alternatives. And that's also happening in India, okay? A lot of discussions, and hopefully methanol economy would take off, okay? So with this, I would like to acknowledge my coworkers, especially Professor, late George Ola. And I had very good people. Alain Gopart is with me. He's a senior scientist in my group for almost 20 years, 22 years. He's been doing a marvelous job. Sri Narayan, my colleague, who is an excellent electrochemist, and all these people who have helped me, work on this project. My students, my institute, my supporters, RPE and others. And this is what I think Vivek talked about. In 2013, we got recognized by Israeli government with a $1 million award. It's like a Nobel Prize in energy. We received this for this methanol economy concept, okay? With that, if you come to sunny California, come and visit California. This is my institute. This was my group about a few years back. With that, I thank you very much for your kind attention. I'll stop share and I'll do a methanol fuel cell demonstration, okay? Okay, now let me go back again. Okay, actually a methanol fuel cell is a very simple device. I'm just going to, can you see this?
Yeah, we can see.
This is called a membrane electrode assembly. A fuel cell is like a battery, okay? I have a membrane, a polymer membrane, which conducts protons back and forth. And I have 2 electrodes on either side, okay? Okay, let me see. This is the anode, and you can see the reverse is the cathode, okay? So what I've done is this membrane electrode assembly, just a minute. I have put it in a little gizmo. And this has an anode compartment and a cathode compartment. And I have let me see. So, this is the cathode. Let me see, a cathode. And it has some holes here. It's an air breathing cathode. On the other side, you have an anode where I can put some methanol liquid in it. And it's attached to a little motor. So what I'm going to do is I'm going to take some methanol and water, which is in this little bottle. And I'm going to take methanol and water and put it into this chamber and see what happens to this little. So at room temperature, I'm adding methanol and water into this little chamber, and it'll start. Yeah. It'll start working now. It makes methanol air battery, which works at room temperature. This was invented by us with a cooperation with NASA JPL in the 1990s. And this technology has been commercialized. 5 kilowatts to 70 watts. You can buy this commercially from Font Fuel Cells in Germany. So methanol could be used to make electricity too. And this is my materials which have been licensed commercially is also, I'll show you here. This is in this bottle. This is produced in multi tons every day for the indoor air capture. And right now we are working with big guys, who do a lot of air cooling of data centers where they're moving air. We are showing them how to capture CO2 out of that moving air. So everybody gets credits for CO2 capture. Okay, with that, I think I'm done and I will be happy to answer any questions from the audience.
Great, great. Thank you very much, Professor Surya Prakash. I think we don't have the audience to clap, but I think it's a really, really exciting talk. It looks like methanol economy is a game changer, and you nicely explained every details of it. I think we all benefited from your very valuable talk. And there are lots of questions now. I think you can take some of them. But before we go to the audience, if there are some questions from the panelists, I can ask them to ask. Venkat, you can unmute and start your video and ask the question.
Yeah, Professor Surya Prakash is an excellent lecture as usual. Okay.
Thank you.
And we are not far behind in India. In ICT, Professor Yadav is doing that CO2 and hydrogen to convert into methanol pilot plant studies. And also then again, methanol dehydration to dimethyl ether. And also in NCL, Pune, they are going on a big way for commercialization of methanol to dimethyl ether. So we are doing already on the methanol economy.
That's wonderful. That's wonderful. Actually, I was also told that Kirloskar has already, the Ashok Leyland has made M100 engines for trucks. And my Niti Ayog friends tell me that they're doing that. And there's a lot of activity. I'm very happy about that India is also looking at it.
That's why I just wanted to tell you that we are.
That's good. Yeah, thank you. Thank you.
Thank you.
Yeah.
Venkat.
Yeah, thanks, Vivek. Thank you, Professor Surya Prakash, for a very, very interesting talk. My question is about the biomass to methanol conversion, because biomass, you have also listed out the processes. So what is exactly the bottleneck in this process for the biomass to methanol conversion?
Biomass, the bottleneck is, capture, actually collecting biomass. Biomass is 90% water. So what you have to do is in small places, you collect biomass and you have to dry it. And you can collect it and convert it at significantly using air and lower temperatures. You can make it into what's called bio-crude or bio-oil, okay? And that has to be brought to a centralized location where you can do, further, oxidation to make syngas, okay? So it's a several step process. But of course, in India, we are pretty green. In fact, India is a lot greener than many other people because most of our, sugar industry, paper industry and all, they burn their bagasse. They use, their biomass already, they're producing heat out of it, right? So you have to convince them to make, more value added products and things like that.
Thank you, Professor Surya Prakash.
Yeah, so before we take some questions from the audience, I have one or two questions, Professor Prakash. So this technology seems to be really a game changer. And you came up with this technology, this concept of methanol economy is more than 2 decades now. So what is
more
it?
Than that.
Yeah. So what is it that is stopping us or stopping everyone to not commercialize it at a bigger scale, right? Because
because the way I tell people is the world suffers from a disease called affluenza. We are too affluent for our own good. Mm-hmm. Because oil and gas was available. We don't see humans, we don't want to change. But change is inevitable. We get old, right? Every day we are getting old and all that. But people don't want to change. So once something is grained in and people adopted this technology, especially gasoline and diesel vehicles, there are 1.5 billion vehicles running on petrol. So to change it, there is a lot of inertia. So my point is, the inertia also is to go to a new infrastructure is very expensive. India talks about electric propulsion big way, but we don't even have, we have blackouts and brownouts in every place. We don't have enough electricity to do that. So we need to come up with it. And also, managing the grid with alternative energies is not easy. So wherever you're producing cheap electrons or electricity, you capture CO2 and then make this methanol and make a liquid. So methanol economy is nothing, it's a disguised hydrogen economy. It's more convenient hydrogen economy.
Yeah.
In fact, George Ola used to say that hydrogen economy is dead, but they have not given it a public funeral yet, because it's difficult to do hydrogen economy. Methanol economy is easy to do, and it's, you don't have to change your infrastructure. Hydrogen economy, you need to come up with a new infrastructure. New infrastructure is very expensive. So these are all the things happening. But the problem with politicians is they may not know the difference between ethanol or methanol. Okay, for them it's alcohol, right? So that's another issue too,
Yeah.
I'm not criticizing anybody, I'm sorry,
Yeah. I have one more technical question before I take this question from other. So you already explained about the toxicity of methanol, that if one can control the dispensing process, then ideally there should not be issue with the toxicity. But methanol is also a low boiling liquid and it can vaporize, and the vapors is also toxic, right? So how do I control?
No, actually when there is air around, it's in closed the environment, it can be a problem. Okay, but methanol boils at 65 degrees Celsius. Even gasoline is also high vapor pressure too. It's not so this thing. But what people have found is, especially in California in the late 80s, we adopted M85 fuel in LA County because it had a smog problem, pollution problem. So we had no problem with dispensing methanol in gas stations. And in fact, China, they have no problem at all. They've already done it. They've already done it in large scale. Only thing is you shouldn't siphon methanol. In India, people siphon fuel, that we have to teach them not to do.
Yeah.
Right? That's the biggest thing we need to educate the people. And of course, you shouldn't drink it because methanol, is very fragrant and apparently tastes good, okay? And it'll kill you. Yeah. You have to teach people, yeah. Okay, so Professor Prakash, thank you very much for all the answers. Now I will take the answers, questions from the audience. So I will make them, the Santosh Singh, I'm going to make you the panelist. You come to the panel and then ask the question. Dr. Santosh Singh, you can accept you're here now, right? Yes, Dr. Santosh Singh, you can unmute and switch on your video and ask the question directly to the speaker. You are muted. Can you unmute?
Yes.
Yes, please go ahead.
Hi, Sir, Professor Surya Prakash. So it was a very nice talk, actually. It was very informative. So in this methanol to hydrogen, CO2 to methanol conversion process, there is a lot of hydrogen is being utilized.
Yes.
So my question was that what should be the source of hydrogen to be used for the generation of methanol in this process?
It should be from water. Water is the ultimate source. Because producing it from natural gas and all that, it's a vicious cycle, right? You're using see, my idea is to keep the carbon underground. Whatever carbon mankind has put, humankind has put into atmosphere, recycle that carbon. Don't take away any more buried carbon, okay? So this methanol economy would let you do that, because we can make everything currently we make out of fossil fuels with methanol.
Yeah, because I asked this question because if we use the renewable energy sources, suppose the solar energy source for the generation of hydrogen, and that also to generate this hydrogen again we need a lot of energy, right? And
I know, but energy, look, solar and wind are becoming so cheap. In fact, in wind energy is becoming so cheap at night time in the United States, they give away. They don't know what to do with it. California is one of the largest states in the union. We are the 5th largest economy in the world. I think about 2 days ago, we made electricity totally carbon neutral. It's possible, okay? So what I'm trying to tell you is wind farms where they're producing wind energy, you capture CO2 and make methanol. And so you need water, of course. But remember, water is a big issue too. But if you look at oil, okay, like one of my colleague actually, you may know his name. His name is Deepu Daman Malhotra, who was at SRI. Okay, he was a chemist, a George Wallace student. He wrote a book called 1 cubic mile of oil. All the petroleum oil is only 1 cubic mile. Okay, so we have plenty of water in the world. Okay, in fact, Baba Atomic Energy Research Center, if nuclear fusion becomes a reality, India is doing this high temperature nuclear processes too. If a nuclear energy becomes cheap, you can split water and make a lot of hydrogen. Seawater, make hydrogen. And hydrogen can be combined with CO2. So you make liquid fuels to keep your infrastructure sane. That's the idea. Okay. So it's not a problem at all, because energy is, in my opinion, sun is going to be there. Sun gives us so much energy. It's free, as far as I'm concerned. Yeah.
Thank you.
Yeah. This was the one question. Yeah.
Santosh, we can come back to you afterwards. Like we have some other questions.
Okay.
And then, so Chetna, can you please ask the question?
Thank you, sir. Thank you, Professor Prakash. It was very interesting and very insightful, and I am very inspired about the talk that you gave about the methanol economy. So as we are aware that whatever thing we are trying, like even with the renewable energies and solar and wind, they are all coming with some drawbacks. So what are the challenges associated with the methanol economy? Because it seems very promising, but there must be something that may be inhibiting its commercial applications or a large scale functionality.
Yeah, because look, what is inhibiting is the way our economies are set. Of course, everybody wants to make a profit, and the companies, big oil companies, they don't want to change because they can make money with the existing investments, right? Oil and gas are huge investments all over the world. And you cannot say time out, no oil and gas, okay? This is where we all have to come together. We have to think differently. So my point is, let us adopt methanol in all kinds of sectors. Then we will have the incentive to make renewable methanol using renewable energy. In fact, wind and solar has so much potential in India. In fact, India is doing a lot of solar. Our solar production has gone quite high in India. They're doing very well. Of course, the solar panels are made in China. And China has COVID and all these problems, supply chain problems. Of course, making photovoltaic panels and all, of course, there's an energy penalty too. So you need to make sure you're not using carbon-based energy to make silica, right? Silicon, amorphous silica, silicon and all that. So these are all the issues. So you have to look at the whole life cycle. This Santosh, it's very important. Okay, so that stuff is, I think it can be done, but it has to be done gradually. I'm not trying to say don't do it. We need to adopt a mixture of technology, not one technology, okay, to solve our problem. And the global warming train has left the station. Earth is going to get warm. We need to come up with mitigation technologies. Okay, that's what I tell people.
Yeah. So this was more about the problems associated with our mindset that we will eventually gradually move to the methanol.
I think we will. Look, necessity is the mother of invention, isn't it?
Yeah.
So we are in that cusp now. Yeah.
And any technical issues also associated?
Sorry, I have to stop you because we have some other questions. So, Professor Sanjay Kumar Singh.
Okay. Thank you, sir.
Yes, thank you.
Thank you, Professor Vivek. Professor Surya Prakash, it was nice listening to you again, because last time you visited IIT Indore in 2019 in the conference.
Yes, I did. Yes.
We had a chance to discuss with you. So my question is, there's so much of progress is observing this, like you have published a lot in this area. So what is the bottleneck, like why the technologies are not coming up, particularly the catalysis processes for CO2 methanol production?
Yeah, see, the catalytic processes exist. In fact, people are not investing to build plants. It's not like a software. I can do it in a garage, okay? Because methanol is a commodity chemical. It has to be produced in megatons, okay, to make it practical, right? So that is the problem actually. But I think in the next couple of years, you will see that this problem is not a problem at all. Capture is not a problem. Conversion won't be a problem. And so what I am telling people is, use methanol, whether it is brown methanol or renewable methanol. India has a lot of, low quality high ash coal. Okay, so gasify high ash coal to make methanol, and also sequester CO2. Because when you burn coal, you can sequester CO2 too. So they can introduce methanol. Once people start using it, there will be an impetus to make renewable methanol because it's good for the world. So this is a gradual process. I am confident it will happen. And yeah, it's unfortunate it didn't happen in George Ola's lifetime. He used to tell me, Surya, this will happen in your lifetime. Now I tell my student it will happen in their lifetime. So we have to be optimists as human beings. We have to be optimists, especially as scientists. We need to be very optimistic.
Yes. Thank you, Professor Prakash.
Yeah, Dr. Hall. Yeah, Dr. Hall, please.
Yeah. Okay. I think Dr. Prakash, you and I have talked about this a little bit earlier, a few weeks ago. One of my key questions is, it's not really a question, is that this seems to be a very game-changing technology. But if you pardon my impression, that this is still at a what you would call a laboratory experiment level. We would like to support, I represent a charitable trust, which is willing to fund a prototype or a pilot plant where this technology now brings into a scalable, commercial, semi-commercial pilot plant, where we can take the pieces of this and see whether it is commercially feasible, what are the various ingredients. And we always find that I'm an engineer, so I'm not a chemical scientist, but we always learn along the way. There are many pitfalls and there are issues that we need to learn. So would you be interested, along with Professor Vivek Pulchateri, to create a pilot plant and select the components of this, maybe not all of it, maybe it's methane to electricity, as well as CO2 capture, as to see how, when you scale it up, what are the pluses and minuses that will occur. And we are ready to fund this kind of activity through our research program at our charter school,
Yeah, sure. Look, the thing, look, I'll tell you what happened. Okay, in Iceland, we built this plant. It was expensive, actually. Any pilot plant, $30 million was spent in Iceland just to build a 12-ton per day. So what these people are talking about is, methanol is a commodity chemical. It needs to be manufactured in large quantity to make it viable. Correct. In fact, what people are thinking is you need to at least manufacture anywhere from 500,000 tons to 5 million tons a year. There are gigamethanol plants people are thinking about. So this is the issue, because of course, the technology works. In fact, it has been demonstrated at certain levels, 12 tons, and China is going to do 1,000 tons a day. George Ola plant did 12 tons a day. In India, if you do it at village level, you have to do probably, 1,000 gallons a day or something like that. You need to think about, then it may not become very viable. That's what I was telling you privately. Maybe we'll talk about this privately later, okay? We'll have another session.
Yeah, but definitely one of the things is that the one in Iceland where they were using geothermal energy. And here in India, I think there are some of the parameters of converting this require different assumptions.
No, we just need electricity. That's it. That geothermal electricity or wind electricity is electricity. That's not a problem. That's not a problem at all. It's the cost of electrons,
Yeah. For example, if we have a very large solar farm, would that be able to support this?
Oh, sure. Solar farm or a wind farm, near Chitradurga in Karnataka, they have a huge wind farm, Yeah.
So that's one of the things that we would like to take forward. Is to
sure. Yeah, we'll talk about that,
But I just wanted to let you know, I really appreciate you giving us sharing your knowledge and everything. And we look forward to taking this. I think Dr. Sanjeev Kumar asked the question, why is it not taking further?
Sure,
I think we are ready to try this, but we need to try it in steps to scale it up. And we would love to.
Actually, you know, other people in India are also thinking about it. Yeah, that's true. Yeah, you're right.
But we're ready to fund an activity where we could do a pilot plant. That's all I want to say right now.
Okay.
Because the rest of it can be taken offline and we can have conversation.
Okay.
I've talked to you and Dr. Vivek also. So we look forward to opportunity to start thinking about such a pilot plant.
Good. Yes, I agree, Dr. Turpule, and thanks for supporting this cause. I think we will definitely take it further. So we will take one or two more questions because already 8 o'clock here. So Dr. Nimai Datta.
Professor Prakash,
yes,
thank you very much for this excellent talk. I have 2 questions, sir. The point is this: the key to this technology, as I understand, is the availability of cheap hydrogen and a cheap way of carbon dioxide capture from the atmosphere.
Yes.
Now, until these 2 key questions are solved, the methanol technology as such, there is no doubt about it regarding its downstream activities. Now, sir, regarding this carbon dioxide capture, this amine process, it appears to be very, very promising and definitely a novel and revolutionary method. But sir, in all homogeneous catalysis, first thing is ruthenium is a very expensive metal.
Sure.
So what is about this ruthenium loss? Have you measured the ruthenium loss and how to recover this catalyst and recycle it? Have you done any work, sir?
Yes, we have done, and ruthenium works, but we don't want, when you want a commercial plant, we don't want to use ruthenium. In fact, what we have done is we've immobilized catalysts in solid surfaces. And once you immobilize it, you can, in fact, even conventional catalysts, in fact, we have a whole program on improving existing copper zinc oxide catalysts with different metals. In fact, we have some very interesting results, which I have not published yet. We can get very high methanol conversions. Not only we make methanol, we can tailor it to make either natural methane or methanol, just by changing the catalytic surface. So we can do Sabatier process or methanol synthesis. And also capture, we are going away from amine. I'm going to publish some papers you will see recently. So this capture conversion, we have solved some big issues because capturing is not so easy. You know, people are spending so much money. When you take sodium hydroxide or calcium hydroxide to capture, you make carbonates. To release CO2, you have to heat it to very high temperature.
Exactly.
So very energetic to release CO2. So this problem, I think you will see. We will publish soon on this kind of stuff. So all these things will be solved because as I started my talk, CO2 capture is a simple acid-base problem.
So my second question is this, regarding this hydrogen, cheap hydrogen. Today also it is a problem because
it is true, but the thing is, if you have cheap electricity, this company like BASF and all, and people in Sweden, they are making 5 to 10 megawatt electrolyzers, huge electrolyzers they are building, using nickel electrodes, which are very cheap compared to conventional platinum electrodes. Okay, so alkaline electrolysis is a very mature area. It is 73% efficiency at at room temperature. So this kind of stuff is happening, and the Chinese are building huge electrolyzers you can buy very cheap. So electrolyzer technology is coming into vogue. So if CO2 capture technology coming into vogue, making methanol is a very simple process. And also remember, government should get involved there because governments have the big pockets.
Okay. Thank you, Dr. Datta. We will take a last question from Srinivas. And Ankush and Ajay, maybe you guys can ask afterwards, right? We have to end because it's already 8:10. So Srinivas, please go ahead.
Yeah, so thanks Professor Prakash for this wonderful and exciting talk, and Professor Vivek for organizing this meeting. It was very insightful, and it has given me a lot of food for thought. So actually I am from Thermax here in Pune, India, and we have recently piloted a plant to convert coal to methanol. So we demonstrated around 4 liters of methanol being produced. So it is around 4 TPD plant that we are planning. So in that one, we also have a carbon capture unit where we are capturing this carbon, but right now we are letting it go. So I have a couple of questions. First one is that what is the best way to make use of this carbon CO2 that we are capturing and converting it into back into methanol? That is first question. And second one was on the capture front. So we were looking at the metal organic frameworks. So how do they stand in terms of capture of CO2, whether that is the right approach to proceed? And the next question is in terms of the overall like the approach that we need to adopt. So any suggestions on like so because we are using fluidized based gasifier and the catalyst to convert syngas to methanol and all. So any suggestions, advice on like what is the best contemporary best approach for converting this coal to methanol? Thanks.
Yeah, coal to methanol, you know, the Chinese have done this they have improved it very well. And in fact, believe it or not, in China, they make methanol at their cost, $100–120 a ton. Okay, that's what they were telling me when I was in China in 2019. So the coal gasification, you know, you guys at Thermax, you know, you guys were doing it. I think you had a Niti Aayog project too on that, you know, on the high ash coal. But the CO2, you also think, because CO2 is, of course, is a pollutant, you know, you produce quite a bit of CO2 in this coal gasification and converting it to methanol. So the CO2 has to be captured. And if you have access to hydrogen, green hydrogen, you can make green methanol, you know. So this is the idea, you know, a renewable kind of a methanol with little bit, it's not totally green. It could be blue methanol, I could say, you know, the gradation. We have put a gradation on this. So this can be done. But the hydrogen production, as we discussed in the previous, you know, this thing question, electrolysis is the best way to make hydrogen. Okay, this is one thing. And also, I think the companies like Thermax, you know, this you're using fluidized bed for gasification. And methanol, if you do under batch process, there are processes where you can increase the, you know, because it's a thermodynamic limitation. At higher temperature, your conversion is less. You know, CO2, H2 to methanol. So you have to operate at lower temperatures. And there are new catalysts coming along. For example, nickel gallium type catalysts, nickel indium type catalysts, you know, oxide catalysts. You can do at lower temperature. So you can also your hydrogen pressure can be decreased. Conventional methanol synthesis, the pressure, hydrogen pressure is 70 bar to 100 bar, you know. Yeah, you can go to lower pressures and all that. So all these things are happening as we speak. And, you know, look, again, you know, we are all learning to crawl, okay, before we walk. And also the funny thing is, we are all in different silos. You know, China has solved a lot of problems, but they're not willing to share with others. If China is allowed to share with others, you know, then we don't have to reinvent the wheel. It's unfortunately, every country is reinventing the same wheel, you know, which is terrible, right? We thought that we have a global, you know, that's another issue too, you know, which I don't have an answer to that. You know, we are becoming very nationalistic and things like that. Is crazy. We should be helping each other, right? We all live in one earth, one world. We are all global citizens, you know. Vasudhaiva Kutumbam, we say in Sanskrit, right? We are one world. Man.
Yes.
Yeah. It's terrible. Yeah.
Thank you.
Thanks. And so just one, I think one question I had. So this metal organic framework, are they?
MOFs are too expensive, you know. MOFs are not a good idea. You need to come up with something which you can make $1 a kilo. MOF is a synthetic gold, you know. Nice, you can publish nice papers, but
publication
you can't do much.
is okay. Commercialization, not at all.
Not, it's very tough, yeah.
Okay. Thanks. Thank you very much. I really appreciate that. Thank you.
Yeah. Thank you. Thank you very much, Professor Surya Prakash, for very exciting talk and also giving answer to all the very important questions. You know, very detailed, unbiased insight. I think we all learned a lot today. I think it's a very good learning evening for me. I guess for all the audience. So thank you very much again, Professor Prakash, for your time. And I know you wake up early there in the United States. So we end here. Thank you very much, everyone, for attending the talk. We will meet again.
Thank you. It was nice seeing you, all of you, and many of you are my friends, so it's very nice. Take care, and hopefully we will meet soon in person.
Yes, we should meet.
Thank you very much.
Take care. Okay, bye.
Okay, bye-bye then, everyone.
Bye.
Thank you.
Thank you, Professor Kantam. Thank you. Bye-bye.
Bye. Bye.
Bye.
Yeah, bye. Thank you. Thank you.